day to everyone. I welcome you all in my YouTube video channel. Today, I will deliver lecture on Pigeonhole Principle, lecture number 5, in which I will solve more problems on Pigeonhole Principle. Now we solve a problem. Problem is so that any set of 7 distinct integers contains 2 integers x and y such that either x plus y or x minus y is divisible by 10. Now we solve this. Let A be a set containing integers a1, a2, a7. These all 7 integers are distinct. Let Ri be the remainder when any element ai belongs to A is divided by 10. Let we have the following partitions of the set A. S1, the first partition, contains all those elements ai of A such that when ai is divided by 10, it gives remainder 0. Similarly, S2, second partition, contains all those elements ai belongs to A such that ai is divided by 10, then it gives remainder 5. And similarly, in this way, we get 6 partitions S1, S2, S3, S4, S5, S6. Since we know that when any integer is divided by 10, it gives remainder either 0, if it is divisible by 10, then remainder 0, or remainder 1, or remainder 2, or remainder 3, or remainder 4, or remainder 5, or remainder 6, or remainder 7, or remainder 8, or remainder 9. Only these are the possible remainders when any integer is divided by 10. If we divide any integer of A, here A1, A2, A3, A4, A5, A6, A7, then its remainder must belong to any one of these SIs. Means 6, S1, S2, S3, S4, S5, S6. Let us consider the 7 distinct integers A1, A2, A3, A4, A5, A6, A7 as pigeons, and 6 S1, S2, S3, S4, S5, S6 as pigeonholes. Then, according to the pigeonhole principle, there exists at least one pigeonhole which contains greatest integer function 7 minus 1 by 6 plus 1 number of pigeons. Means 7 be the number of pigeons and 6 be number of pigeonholes, and this is equal to 2. Therefore, at least one pigeonhole which will contain at least 2 pigeons. Since by division algorithm we know that ai equal to 10 qi plus ri. Here qi be the quotient and ri be the remainder when ai is divided by 10. Similarly, aj equal to 10 qj plus rj. rj be the remainder and qj be the quotient. Since here we see that a particular pigeonhole contains at least 2 pigeons. Here pigeonholes are S1, S2, S3, S4, S5 or S6, and pigeons are numbers A1, A2, A3, A4, A5, A6, A7. Let AI and AJ be members of any particular SI. Means that may be either in S1 or S2 or S3 or S4 or S5 or S6. Now AI minus AJ equal to 10 multiply QI minus QJ plus RI minus RJ, and AI plus AJ equal to 10 QI plus QJ plus RI plus RJ. This is number 1, this is number 2. If Ri equal to Rj, then from 1 this will be 0. Therefore Ai minus Aj equal to 10 multiply Qi minus Qj. This means 10 divides Ai minus Aj. This is number 3. If Ri not equal to Rj, means remainders are not equal. Here we see this may be possible in S3, S4, S5, S6. Here in S3 we see if Ri equal to 1 and Rj equal to 9, then Ri plus Rj means 1 plus 9 equal to 10. Similarly here also we see that if Ri equal to 2, Rj equal to 8, then Ri plus Rj, that is 2 plus 8 equal to 10. Similarly if Ri and Rj are distinct, then Ri plus Rj equal to 10, because Ai and Aj belong to any particular Si. They do not belong any two separate Si, and therefore we get Ri plus Rj equal to 10. Therefore from 2 Ai plus Aj equal to 10, Qi plus Qj. Here Ri plus Rj equal to 10. Here we write 10 and we take common. This is 10 multiply Qi plus Qj plus 1. Therefore 10 divides Ai plus Aj. This is number 4. Therefore from 3 and 4 we see that 10 divides either Ai minus Aj or Ai plus Aj. That is Ai minus Aj or Ai plus Aj is divisible by 10. Now we solve the next problem. Problem is in a tournament in which each player plays against every other player and each player wins at least once, so that there are at least 2 players having same number of wins. Now we solve this. Let number of players equal to n. Any particular player will play with remaining n minus 1 number of players. Given that each player wins at least once, therefore it will be at most n minus 1. If any particular player wins with any other particular player, number of wins equal to 1, and this same player wins with any third player, then wins will be 2, and in this way at most number of wins may be n minus 1, because he plays with remaining n minus 1 number of players. Except him, remaining number of players be n minus 1. Let A be the set of n players. This set containing player P1, P2, Pn. Let we assume this as set of pigeons. Let B be the set of wins. At least one win be 1, and at most wins be n minus 1. So wins be 1, 2, 3, n minus 1. Let this is the set of pigeonholes. Here we get number of pigeons be n, number of pigeonholes be n minus 1. Therefore, according to the pigeonhole principle, at least one pigeonhole contains n be number of pigeons minus 1 by number of pigeonholes n minus 1 and greatest integer function plus 1, and this is equal to 1 plus 1 equal to 2 number of pigeons. That means one pigeonhole contains 2 number of pigeons, means pigeonhole be number of wings here. So 2 players will be in a pigeonhole, means wings, same wings. So at least 2 players have same number of wings. Proved. Now we solve the next problem. Next problem is, so that any sequence of n numbers must contain a subsequence whose sum is divisible by n. Now we solve this solution. Let this is a sequence. This sequence contains elements c1, c2 dot cn. Number of elements be n. Let us consider subsequences of this sequence be a1 equal to a subsequence containing only element c1. Second subsequence is a2, which contains element c1, c2. Third subsequence be a3, which contains element c1, c2, c3. In this way, nth subsequence an be a subsequence such that it contains elements c1, c2 dot cn. Let this is number 1. If sum of the members of any particular subsequence is divisible by n, then our problem is solved. That is, our proof is done. But if sum of the members of none of these sequence is divisible by n, then in this situation, if sum of the members of any subsequence is divided by n, then possible remainders will be 1 or 2 or 3 or n minus 1. Already we have seen here that if a sum of the members of any particular subsequence is divisible by n, then remainder will be 0. Here sum of the members of subsequences be not divisible by n, then remainders will be 1, 2, 3 n minus 1, not 0. So number of possible remainders equal to n minus 1. Let set of these remainders be the set of pigeonholes. We compare this. Set of remainders with set of pigeonholes. Let here we have n number of subsequences. Let collection of these subsequences be denoted by collection of pigeons. Here number of subsequences be n, therefore number of pigeons be n. This is the set of pigeons a1, a2, an, and this is the set of remainders 1, 2, 3 n minus 1. Here we have not taken remainder 0 because when divisible by n, then remainder 0. Here not divisible by n, that is remainders will be 1, 2, 3 n minus 1. Therefore, pigeonhole principle, we get there exists at least one pigeonhole which contains here number of pigeons n minus 1 by number of pigeonholes, and we take greatest integer function plus 1 number of pigeons in at least one pigeonhole. That is, that pigeonhole will contain 2 pigeons. Value of this is 2. Therefore, 2 subsequences correspond to same remainder. These are remainders. Let these subsequences be AR and AS such that S greater than R. Since AR be a subsequence which contains element C1, C2 CR, and AS be another subsequence whose elements are C1, C2 CS. Here we have taken S greater than R. When sum of the elements of AR be divided by n, it leaves remainder T. That is, by division algorithm, C1 plus C2 plus plus CR equal to n QR. QR be the quotient plus T remainder. Similarly, when sum of the elements of AS is divided by n, it leaves same remainder T. We may write C1 plus C2 plus plus CS equal to NQS plus T. Same remainder when these are divided by n. Let this is number 2 and this is number 3. Now we subtract 2 from 3. We get C1 plus C2 plus plus CS minus C1 plus C2 plus plus CR. And right side T vanishes, only remains n multiply QS minus QR. Since S is greater than R, so left side remains CR plus 1 plus CR plus 2 plus CS, and right side be same. This means n divides CR plus 1 plus CR plus 2 plus CS. Let this is number 4. Therefore, we get a subsequence containing elements CR plus 1, CR plus 2, CS of the original sequence containing elements C1, C2, Cn, such that sum of the members of the sequence is divisible by n. So, any sequence of n numbers must contain a subsequence whose sum is divisible by n. Proved. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.